Hi there, and welcome to today's webcast discussing OpenFlow version 1.3. My name is Leslie Denson, and I'm joined today by Steve Brar, Manager of Global Product Marketing for HP, Mike Haugh, Senior Manager of Market Development here at Ixia, and Toshal Dudhwala, Product Manager, also here at Ixia. We have a great session planned for you today, and Mike will start off by talking about how the latest enhancements in OpenFlow technology can help your business. Toshal will be just showing us a live demo of how you can test OpenFlow in your environment. And building from that, Steve will discuss how HP is leveraging OpenFlow in order to improve their experience with Microsoft's Lync collaboration suite. One quick item before we get started. We will be taking questions at the end, but if you find that you have a question during the presentation, go ahead and submit it via the Q&A feature, and we'll aggregate those to make sure they get answered once we're complete. Without further ado, I'll pass it along to Mike to kick us off.
Thank you very much, Leslie. And we have a packed agenda for you today, so we'll get started here and move along at a pretty fast pace. If we just advance to the next slide titled OpenFlow Fundamentals, one of the first things I just want to kind of bring everybody on the call up to the same level in terms of a basic understanding of SDN and OpenFlow before diving into some of the specifics about version 1.3. So first and foremost, we hear a lot about software-defined networking, and there's a lot of different flavors out there, and there's many different ways to approach it. But in general, software-defined networking at a broad description level, it is an emerging new architecture. So it's a paradigm shift from traditional networking, where you have a separation of control plane and data plane. And that in and of itself is not so unique. There's been many network architectures in the past with centralized control. However, there are quite a few things that are unique about it. But I think part of the question we ask is, well, why now? What's wrong with networking today? And when you look at distributed protocols like BGP, OSPF, ISIF, they work extremely well in the internet backbone. And they're running networks today. However, they're lacking the control, and it's slow to enable new protocols and features since they have to go through standards bodies, and then each vendor has to implement them. So essentially, it's very slow to develop and deploy new features in the network that can benefit the service providers and end users of the network. So SDN describes three layers. You see the picture here on the right. At the top, you have the application layer. This is where the software exists that has the logic to control things required of the network. Then you have a middle section, which is the control layer, or commonly referred to as the controller, which we'll get into. But at this layer, you have the control layer, and then the control layer is talking down to the network layer, the network infrastructure. So one quick analogy I like to use is this kind of architecture is similar to the control layer and infrastructure layer is like a controller on a router or switch, and the infrastructure is like the line cards. You're essentially centralizing the control plane. So what are the benefits of this architecture? One is that it makes the network programmable. And by programmable, we meaning down to the application level or flow level to differentiate different traffic streams and treat them differently on the network, steer them differently, different levels of QoS. It also, as I was indicating, adds an element of makes the network agile and fungible. It makes it flexible to implement features and functions very quickly, because as long as the lower layer programming interface supports it, you can tell the network to do anything you want within those bounds. It makes it centrally managed. A lot of service providers and data center operators like this concept, where they're not trying to figure out what all the routers and switches states are in the network. It's very well known because it's been programmed and it's centrally managed. I mentioned this concept of programmability. If you click the advanced one tick, you'll see a red circle appear around what's known as the southbound API, this API from the control layer to the network infrastructure. And by using a well-defined, open standards-based control layer, you can program the network as you like, and you can use multi-vendor implementations. And so this is certainly a benefit to having essentially kind of a common language to talk to the network with to program it. Please advance to the next slide. The second slide on OpenFlow fundamentals is really just talking more specifically on OpenFlow itself. So I like to describe OpenFlow as an SDN enabling protocol. So in and of itself, OpenFlow is really just that southbound API piece. OpenFlow does not fully describe all the controller functionality. OpenFlow doesn't describe all the application functionality. It's really just the API or programming language to essentially program the network. OpenFlow was developed at Stanford and Berkeley, started back in around 2007, and since in 2011 or so, the intellectual property rights were transitioned to a standards organization called the Open Networking Foundation, or the ONF. That's why essentially anyone involved with OpenFlow now is usually a member of the ONF. And it's a member-based organization with over 90 leading companies. Ixia was the first test company to join and is very active within the ONF. So looking at OpenFlow specifically, you have really two main elements in terms of where the protocol is exchanged. You have the controller, which is usually a centralized element, and then you have all of the OpenFlow-enabled devices, usually referred to as OpenFlow switches. And between them, you have a OpenFlow channel, which is usually established from each switch up to the controller. So this channel of communication it will run over TCP. It optionally can be secured with TLS or SSL. It can be an encrypted channel. Then essentially what you have is the controller at a very fundamental level pushing down rules or controlling the forwarding of the switch. It does so by populating something called the flow table with match and action criteria. So this is one area that's getting much more complicated and robust as we move on to 1.3. But essentially you have match criteria, and then you can perform a single action like forward that packet or drop that packet, or you can perform a list of actions like modify the QoS and then forward, or add a VLAN tag and then forward. So when we say match and action, it can be multiple match fields as well as multiple actions, and that is actually enhancing quite a bit with 1.3, which we'll get into. The controller also has fundamental capabilities of doing configuration and statistical requests down to the switch. So it can read the configuration of the switch, the port information. It can check port states. It can check flow table states, things like that, to essentially understand that how the switch is functioning. So moving on to the next slide, I want to just very quickly take a look at the OpenFlow progression within the ONF, because I think there's some confusion out there about OpenFlow and what versions are out there and available. OpenFlow essentially became available or started becoming available in open source implementations around 2009 with the emergence of the 1.0 standard. That came out of Stanford. In 2011, Stanford released or produced the version 1.1. The version 1.1 was the most current version when the ONF, the Open Networking Foundation, was started. Since the Open Networking Foundation has started, it now is taking this standard and progressing it. So the first update it produced was version 1.2. But vendors very anxious and interested to get into OpenFlow were kind of saying, well, what version do I implement? So most implementers started with version 1.0. It had been around the longest and it was available. And the ONF then decided to guide implementers towards 1.3, but said, look, we've released 1.2. However, 1.3 will be a stability release. We'll only make minor enhancements to it, but we want the next move of implementers to be 1.3. And as we'll discuss going forward, that's basically what's happened is that there are only some limited software versions of 1.1. There are very limited implementations of 1.2. And now 1.3 is becoming the next major version that most vendors are supporting, including you'll see most announcements coming out of ONF members have indicated version 1.3 support, either available or coming this year or soon. So progressing, there have been some minor updates with 1.3.1, 1.3.2, and 1.3.3 is upcoming from the ONF. Another standard I have mentioned here, I won't go into details about it, but one misnomer about the ONF is that it's OpenFlow only. And what I would say is the ONF, from a southbound API or protocol standpoint, is OpenFlow only. ONF is taking on many other activities, one of which is configuration and management. So developed and released a specification called OFconfig, and that has now progressed to version 1.1.1. On the right-hand side here, you see a list of the ONF working groups. And just to point out that, again, the ONF is working on many things beyond just OpenFlow. There's an architecture and framework group working on the whole picture, beginning to look at northbound API as a controller talks to applications, and many other areas. One I'll bring up is testing interop. I'm the chair of that committee. I work quite actively within the ONF and leading that. We're doing things like, plug fests, building a conformance program, working on defining benchmarking methodologies, and other activities. So, the ONF, many of you are probably member companies. You can follow what they're doing at opennetworking.org. Next slide, please. So in this slide here, I want to just give a quick overview of some of the protocol messages OpenFlow uses. First, with controller to switch messages, you have a features exchange. What I'll do here is kind of talk to the bounce diagram or ladder diagram on the right-hand side, which is between a controller and switch. Usually the switch initiates a TCP session, and then over that TCP session, there's a hello exchange. So hello exchange is a symmetric message that indicates the version supported by the switch. And then if I say I'm 1.3, the controller can come back and say, okay, I'm 1.3, and progress with the OpenFlow session, the OF channel itself. If it's indicated in version 1.0 or version 1.1, the controller may reject the session and close the OF channel, or may proceed. But the OpenFlow hello purpose is expressing the OpenFlow version. Then it goes through a feature request, feature reply. This indicates some basic capabilities that the switch is capable of. And some of this has actually changed in 1.3, which I'll go into. Once the feature request reply is completed, then there is a periodic echo request, echo reply, which will keep the OF channel open. This echo exchange can be initiated from the switch or the controller or both, so it may actually go in both directions. So once those have completed, the OF channel, it remains in an up state, and then the controller can proceed on with configuring the switch. So it can push down the flow table entries. These are done through flow mods, so it can be an add, a modify, or a delete of a flow table entry. It can do things like read state, so it can get configuration information. It can get statistical information from the switch. There's a mechanism known as a packet out, where the controller can send a packet to the switch and tell it to do something with it, like forward this packet out all of your interfaces. There's a message called a barrier. A barrier is used to indicate the switch can send a message, like a number of flow table entries, and then it uses a barrier with a transaction ID to query the switch to say, have you processed all of those messages I just sent you? And the switch will reply with a barrier reply with the same transaction ID. So this is kind of one of the mechanisms OpenFlow uses to ensure the switch has processed those messages. So one thing I've indicated here, this role request is with 1.3, one of the changes I'll discuss is the capability of having multiple controllers. But kind of moving on down here, asynchronous messages that occur come from the switch typically, can come from the controller as well, but a packet in is a packet that is received usually on the data plane of a switch, OpenFlow switch, and it either has a rule or a table miss and can send that packet up to the controller. So by sending it up to the controller, it can make a decision to what to do with it. Maybe it uses that packet for learning and pushes down a flow add. Maybe it uses it for a security policy or something else. A switch can also send up a flow removed message. Maybe there's a timeout configured where flow entries will time out if not used, similar to a MAC address table. Switches can also send port status indications. So if a port on a physical switch goes up or down, it can indicate port status changes. There's also a whole host of error commands, and with those error messages, there's also sub-commands to indicate more detail about the error. And I discussed already the hellos and the echoes. And Experimenter, one thing that's important to point out is that OpenFlow, especially into 1.3, is designed to be very extensible. You know, your match and actions are extensible, your statistics are extensible. That allows vendors to develop features on top of OpenFlow that may eventually make it into the standard or may just be vendor differentiation. Next slide, please. So the next slide is a build-out slide that highlights a few of the more significant changes for 1.3 specifically. And when I discuss features in 1.3, some of these may have been added in 1.1 or 1.2, but really the purpose of this presentation is to say, here's what's in 1.3 as compared to 1.0. So I know there may be some folks out there go, oh, that was added in 1.1 or 1.2. The first bullet is I discussed that initial handshake, which there used to be a pull of information about the switch initially that was part of that handshake. That has now been separated out in 1.3, where there's an explicit get config function. So this adds more capability of the controller to query more details about the switch and query those details on demand whenever it needs to. This is good, but it has caused some issues in testing where the switch is now dealing with more requests coming in from the controller. If you click next for me, the next bullet is the fact that 1.3 addressed a fairly significant limitation of 1.0, which is 1.0 defined a single controller. Well, 1.3 formally defines the ability to have multiple controllers. You can have controllers in master, slave, or in equal role. And of course, this is for redundancy and resiliency. And what we're seeing is controller vendors are either implementing controllers in a cluster where the redundancy resiliency is kind of hidden from the switch, or they're implementing this method defined in 1.3 where there are master slaves or equal for redundancy resiliency. Next bullet, please. This next point defines a feature added in 1.3 which defines multi-part messages. So this, again, is trying to help deal with the issue that in many cases the switch is trying to send a lot of information to the switch, and it wants to ensure the switch can process it all. And one way to do that is to break up messages into multi-part messages, send each part separately, and then indicating there is more content in that as part of a multi-part message. So the more flag indicates more is coming, and at the end it will complete all of it. And there's a new mode the switch has to indicate if the switch is being overrun with messages. It can say error, buffer overflow, and the controller will know to retransmit those messages. If you go to the next bullet, please. Another element added to 1.3 is the definition of auxiliary connections, or aux connections. And these are intended to be helpful to improve the switch processing and to exploit parallelism of most switch implementations. So what we're seeing is aux connections are not widely implemented at this point, but it adds the ability for the switch to offload some processing or offload some management functions that may not be handled over the OF channel itself. Click on the next build out is OpenFlow 1.3 defines logical ports. So this is a pretty significant addition because logical ports are higher level abstractions the switch uses for methods like mostly hybrid scenarios like tunneling or link aggregation groups or pointing to loopback interfaces. And this just kind of tells the OF process to send a packet out to a logical port, which happens to be a tunnel interface or some other function on typically a hybrid device. If you go to the next slide, please. In OpenFlow 1.3, there were a number of changes to the flow table, the most significant being that 1.3 defines multiple tables or a multi-table implementation and the ability to pipeline packets from table to table. And with that, you can have the ability to perform multiple actions. So you might use table 0 as your security table, implementing kind of like access list functionality. You might use the second table as like a load balancing or something else. And you might use a final table as your table that you're deciding the forwarding of the packet. So this really expands the functionality of OpenFlow in one respect, but it also causes a lot of challenges for hardware-based implementations to actually support multi-table. So, I won't go into a lot of details with this, but it is important to know that, quite a few of the implementations we're beginning to see are supporting multi-table, but it may be limited. Maybe they're limited to 3 tables, maybe limited to 2. some initial implementations of 1.3 may only be limited to a single table. So it's important to know. Go out to the next point, please. So another very significant addition is the fact that when you look at the match fields that OpenFlow can take action on, we're going from 12 fields in 1.0 to 40 fields in 1.3. So this consists of 13 mandatory fields that you have to be able to perform match on, and 27 optional fields. And of those 40 match fields, those are only the well-defined ones. In addition to well-defined, it's also extensible. So there can be additions to that function. But some very important components added for 1.3 include MPLS header, provider backbone bridging header, and as well as IPv6 header fields. So all of these are considered optional, but very important when you look at various carrier applications that get beyond the data center. Next, fill out, please. 1.3 also adds group table. And again, we saw kind of limited support for this function in the implementations tested at the PlugFest. But basically, a group table is kind of what it sounds like. It's allows actions to a specific action bucket. So applications like multicast, possibly load balancing, fast failover may leverage a group table where you can have a group of interfaces associated with actions that you're taking. Next, please. The final build-out on this slide is 1.3 adds this concept of meter tables. So metering is a very rudimentary method that allows vendors to implement QoS. So through metering, you can do bucketing and essentially meter different traffic and implement QoS policies. So this is a good step in the right direction, but doesn't expose all the functionality usually in hardware associated with implementing queuing and rate limiting. So this is an area where the extensibility group is looking at enhancing or extending OpenFlow to have better implementations for QoS. Next slide, please. So in this next slide, titled OpenFlow 1.3 Changes to Statistics, it's really more about the read state messages. So existing OpenFlow had the ability to do read states on the description of the switch, the flow table, the aggregate flow table, individual port stats and queue stats. Well, this all had to be extended for support of the new features. So what you'll see in this list here, you have group stat and group config, meter stat and config, table features, port descriptions, experimenter extensions. So really, when you think about how the controller interacts with each switch, it needs the ability to pull configuration and statistics for all the functions implemented. Next slide, please. So another very important thing I'd like to point out, especially getting into the topic of testing, is that when you think about OpenFlow platforms, there are many different platforms OpenFlow is being implemented on. So the first that are available in the market, and still some that are quite popular, are software-based implementations. This can be vSwitch implementations or implementations running on hardware but doing all the OpenFlow processing in software. So when you implement OpenFlow in software, usually it's full-featured. However, it's limited performance. You're usually process switching the packets, so you may be limited by the CPU and resources available for forwarding. So software-based implementations are usually relatively low cost, and in many cases you enable it at the edge of the network. If you think of a vSwitch, it's all the way on the server, it's at the edge. Some implementations are using OpenFlow completely at the edge and then mapping data plane traffic onto a tunnel and tunneling over a existing core. That's one example. In the middle box, you can see existing routing and switching platforms. So many existing routing switching platforms, as well as off-the-shelf switches, now have the ability to enable OpenFlow or put a pure OpenFlow operating system on the device. So with these, since you're leveraging existing chipset built for Ethernet and IP, they may have limited features, meaning they won't support all the match in action. They may have limitations of the combinations of match action. So usually limited feature, and then sometimes limited performance as well, because it may fill gaps with doing some things in hardware forwarding, some things in software forwarding. It's really important to understand the application of that switch and the trade-offs in terms of functionality and performance. So these vary a lot in price, but really it comes to you can buy off-the-shelf cheap switches, but they'll be pure OpenFlow, and you can enable OpenFlow on existing routing switching platforms, but there would be essentially kind of no cost savings if you're looking at that from a CapEx, OpEx standpoint. The last bucket is hardware-based switches, which is new chipsets that are built for OpenFlow. So there aren't a lot of these in the market today, but quite a few chipsets like network processors or programmable chips have the ability to support OpenFlow, either full featured or purpose-built, and it's usually very high performance. The issue is when you go to that kind of model, you end up in a higher cost for the device than traditional routing switching. So you get very deep OpenFlow functionality, but you may have a trade-off of a little bit higher cost in your network infrastructure. So moving on to the next slide, I think I only have one or two left before we get to Toshal, is OpenFlow testing. I just want to highlight that at the last Plug Fest from the ONF, we went through a number of test cases from Layer 2 VLAN-based, IP and IPv4 and IPv6-based, MPLS-based testing, and we had a lot of progress. Actually, a lot of things worked quite well. We found quite a few issues, and those are being documented in a technical document as well as a white paper that are produced by the ONF. So keep a lookout for that. If you click next, there's one final build-out on the slide, which is that the ONF it launched a conformance program. So this is to ensure implementations are abiding by the standard. So 1.0 is launched now. The first vendor is going through certification this week, and the 1.3 certification is in progress. So as we advance to the next slide, I'll introduce Toshal Dudhwala, who's going to take us into some details on testing OpenFlow. Toshal?
Thanks, Mike. Good morning or good afternoon, everyone. My name is Toshal Dudhwala. I'm a product manager here at Ixia. We are almost 30 minutes into this webinar, so I'll be very brief on the solution, and I'll show you a quick demo of the Ixia OpenFlow solution as well. So if you look at any OpenFlow solutions, there are three components, or any solutions with three components, and they kind of basically complete the testing for any protocol or any solution. So the first one would be the conformance, and Ixia provides the application called IXAnvil, which basically allow users to validate and confirm conformity of their switch to the ONF 1.0 standard as well as now 1.3. This also allows you to basically make sure that before you send your switch for certification, your switch is basically conforming to the standards. The second aspect of any testing would be the performance and scalability. So Ixia has this IX network application, which is our flagship application. It has a support for various protocols, and OpenFlow is one of the solutions or protocols we have developed in that product. As part of that, there are two flavors. One is the controller emulation, where Ixia emulates a controller, and then it can talk to a variety of OpenFlow switches in the network, including hardware as well as the software switches. And then the other aspect is the switch emulation, where an Ixia test board can emulate hundreds and thousands of emulated OpenFlow switch, which will help you validate the performance and again the scalability of a controller. I have a short demo which I'll be showing you a Ixia 1.3 controller talking to an HP 1.3 switch, and I'll be covering more details on that controller emulation in a demo. And the third aspect of any testing would be the benchmarking. So as a user, when you are going through a various code base in your development cycle, or as an end user of OpenFlow solution, you want to make sure your solution or the OpenFlow protocol implementation is benchmarked to a certain level to either your internal requirement or to your customer requirement. So Ixia provides what we call a quick test, which are a pre-canned methodology test, which allow you to basically benchmark your OpenFlow solutions and OpenFlow network as well. Today, Ixia provides two platforms to basically help customer validate their solutions, whether it's a hardware or a software switch. So same thing could be applied to the OpenFlow solution as well. We have our what we call our hardware platform, which is our XG 12-slot chassis, which has a hardware offering from 1 gig all the way to the 100 gig. Similarly, we also have our software test port, which will allow you to test a software agent or software switches inside a hypervisor as well, where Ixia endpoints can be deployed behind those virtual switch, and then you can validate, again, the performance and scalability of those virtual switches as well. So for today's demonstration, I have a very simple demo. I have 4 Ixia port connected to an HP switch, where one port will be emulating a 1.3 controller talking to an HP switch, and we'll be pushing down various flows with match and actions, and then we'll be performing a proactive failure from a controller, and then we'll measure how fast the switch is reacting to that failure in a way that how fast it's processing those flows to react to the failure, and then we'll measure the convergence time. So with that said, let me show you the demo. So this is our Ixia IX network applications. I have an OpenFlow controller running, and it is connected to the HP switch, which is a 50001. Currently, my connection is up, where we can see that from our statistics. We can also check that on the controller as well. So on the controller, my connection is established. On the switch, my connection is established to a controller 50002, which is the Ixia emulated controller. Now, from this controller, you can define varieties of flows to validate the switch functionalities as well as the scalability. So here I have 4 different type of flows defined. In the first one, I have IPv6 as a match. So here in Ixia, we exposed all the 40 match fields which Mike mentioned before, and then you can not only specify all the match fields, but then you can also, by putting an asterisk, you can also wildcard the fields which you do not want your switch to match upon. We also support the masking as well. So if you want to match on a partial address or subnet, you can also specify the mask as well. So here I'm asking switch in the first flow to match on the Ethernet source with the Ether type of IPv6, and then I have those IPv6 addresses defined here. So from here I can push down the flows. Now, one of the big advantage of Ixia is it allows you to validate and send a large number of flows with just a single click. So when I enable this flow, I have specified 100 flows within this range, and as soon as I enable this, the Ixia emulated controller will send 1,000 flow mods add to the switch. And by clicking this button here, configure range, you can also see what kind of flows we are sending from the switch as well. So when I go on the switch, we can validate that what flows are installed. So on the switch, we have those 100 flows installed now. But in a real world, controller can also request switch to basically send all those flow messages. So we can do the similar thing from Ixia controller as well. We can go to our learn information, which shows you all the connected switches here, and from all the OF channels which are connected to our controller, we can generate an on-demand message. So here I will send a flow stats, and in this one, basically I will ask the switch to send me all the flows it has in its table. Similarly, you can also send other stats requests to the switch here. You can send things like description stats or port features. So I will also send a port feature from here. So in the learn info records here, you can see we have received those 100 flows from the switch. And if I click on a flow stats tab, you can see those 100 flows which are installed on the switch in the IX network GUI itself. And these are all the match and actions we have set on the switch side here. Now, remember, on this one, I have only specified so far the match. In order for us to basically do or tell the switch which port it should be sending the packet out, which I have specified in my action here, we can go back to our learn information, and in the port feature, you can basically see what are the port numbers switch is advertising. So in OpenFlow standard, OpenFlow also defines the port number which are different than the actual physical port of the switch, and this basically allows users to create a logical ports inside a physical switch as well. So like an example on that switch, this is the physical port, but the corresponding OpenFlow port number is 131. So if I go back to my controller, in the instruction set, I have asked that switch to send the packets out on the 132, which is the output port of the switch. So let's make sure that once you send the flows, let's make sure the switch is basically matching on all the required parameters and then performing those actions. So I have this another flow defined here, which is doing a DSCP remarking. So I have asked, I've basically instructed the switch to match on the DSCP value of 46, and when it does that, change the value of that to 22, and then send the packet out on the port 132. So I have already configured a traffic item for those endpoints which are sent by the Ixia controller, and I will start that traffic. And at the bottom window here, you will be able to see what kind of flows are going through the switch here. So the traffic item level, we will be able to see all the packets are being sent and received at a high level. And then we can also go and use an Ixia ingress and egress technology to basically view what value we were sending and what value we are expecting on the egress side. So in this view, you will be able to see that we were sending a value of 46, and as a matter of fact, the switch is indeed remarking that packet and then sending that packet out with the new value of 22. Now going back to our original demo, I also have this flow defined where I have some primary and secondary flows. In this case, I have a third port connected to the switch, and that third port will be sending the packets out on port 133. So I will go ahead and enable that. Now before that, I will stop the traffic. So I will go and enable those primary and secondary flows. So on the switch, I have two different flows defined, and based on the priority, the switch will basically send the traffic out. So I go back here, I will enable my convergence traffic, and now we also want to measure how fast the switch is switching from primary to secondary. So we provide this, what we call our data plane events and rate monitoring. Using this, it will give you a one-click stats in the IX network stats window here, which will give you the convergence time of the switch. So now I have that switch stats enabled. I will go and start the traffic. So again, at high level, all the traffic is going through. Now in order to see which port is receiving the traffic, we can go and do a drill down for received ports. And this will show you traffic on which port the traffic is coming in. So we should be expecting the traffic to coming in on the host port 2, which is connected to the port number 132 of that switch. Now what I will do is I will go and perform a proactive failure from the switch. So when I remove that primary flow, I'm expecting switch to the secondary flow, and I expect the traffic to coming on this host port 3. So I will go ahead and remove that flow from the switch. So when I disable that checkbox, controller will send a flow mode delete, and then we expect switch to remove that traffic. As you can see now, the traffic is now switched on the secondary path, and we are receiving that traffic on the other port. Now remember, we have enabled that data plane convergence stats. So I can now go into my destination endpoint view, which will allow me to measure what was the convergence time. So here we can see the data plane convergence time of that failure was 11 milliseconds. That is an impressive number we have. And luckily there was no packet loss during that failure as well. What we can do is we can clear the stack and we'll restore our original primary path back. Again, and we expect the switch to go back to the original port. And during that, we should be able to see, again, no packet loss. And this time the convergence was 12 milliseconds, which is similar to what we have received before. So again, using the Ixia IX network and IX Enable solution, you will be able to validate not only the performance and scalability, but also the each and every features of your switch as well. I will be now passing the ball to Steve Brar, where he will be taking us to some of the case studies and how HP is using OpenFlow and providing solutions for their customer. Steve, over to you.
All right, thanks, Toshal. I'm going to spend a few minutes here talking about what HP is doing around SDN and how we're taking advantage of OpenFlow to enable new SDN applications for networks. So just to start off, I wanted to share a few data points around some of the investments that HP has been making in SDN over the past several years. HP really started working on OpenFlow back in 2007, working with the academic community, including Stanford University, on Ethane, which was a project that was a predecessor to OpenFlow. And in 2008, we demoed that software on one of our commercially shipping switch platforms at that time. And over the course of the next couple of years, we continued to work closely with the academic and research community to grow the number of customers using that OpenFlow software on our platforms for testing and research purposes. In 2011 is when the Open Networking Foundation was formed. HP was also one of the founding members of the ONF, who now is driving the OpenFlow standard. And then we also delivered at that time that OpenFlow version 1.0 software to our customers in terms of making it generally available on several of our switching platforms. And then just last year, we expanded our SDN offering to include not just OpenFlow support at the infrastructure layer, but also an SDN controller and several key SDN applications. So I wanted to highlight some of the accomplishments that we've made since 2012 to 2013 in terms of expanding our portfolio support for OpenFlow and SDN. So at the end of 2012, we had OpenFlow support across 25 different switch models in our portfolio, which represented over 15 million installed ports in the marketplace. And that's software that our customers can simply go download for free from the HP website and update on their switch devices to get that support. We also initially announced our SDN controller with 3 applications that we were working with customers on. One was a virtual cloud, which is data center virtualization and automation, Sentinel, which is a security application, and a load balancing application that one of our customers is developing on top of our controller. And then in the first half of this year, at the Open Networking Summit, we expanded our OpenFlow support to now over 40 switch models in our portfolio, and that spans the campus and data center from the core to the edge, and it represents over 20 million installed ports in the marketplace. We also introduced a couple new use cases and applications, one around UC&C and Microsoft Link, and one trial with Intel and Verizon around wide area network bandwidth provisioning. And just this year at the Ethernet Innovation Summit, our Sentinel security application won an award for the best SDN solution. And I'll share a little bit more detail around what Sentinel does in this presentation. So I wanted to highlight, just reinforce what Michael presented earlier around the definition of SDN. There's a lot of companies out there that are attaching the SDN messaging to their offerings, and what we decided to do is to go back to the ONF definition, similar to what Ixia was presenting earlier, and align our solution around the industry definition. And this was a definition that the ONF put out back in last year actually, with various different companies contributing. And essentially it's the separation of the control and data plane with applications abstracted. So if you take a look at what that looks like, that framework, you have the 3-layer infrastructure, control, and application. And here we have it mapped to HP's solution. So again, today we have 40 switches with OpenFlow support representing over 20 million ports. We introduced our virtual application networks SDN controller last year, and currently that's in beta and will be available for general release later this year. And then we've demonstrated or have in beta several different applications which I mentioned. And one of the unique things about HP's strategy around SDN is, and what we call it is virtual application networks, is that it actually extends beyond just the 3 layers of the SDN architecture. One of the things that we recognize is that customers may not have OpenFlow-enabled hardware today, or they may be transitioning to OpenFlow. And one of the key elements in today's networks is the management layer. And so part of our strategy incorporates the management layer and includes our Intelligent Management Center platform, which provides a single pane of glass management across the entire network infrastructure, and now also the SDN control plane as well as application layer. And within IMC, we have several different modules. VAN Resource Network or Network Resource Automation and VAN Server Connect are modules which deliver some of the benefits of SDN in terms of automation and agility in the data center without necessarily requiring OpenFlow support today. And then VAN SDN Manager is a module which provides that visibility, monitoring, performance monitoring, and control across the SDN controller, as well as the APIs that the SDN applications are built on. So with IMC, you get a tool that provides a single pane of glass across your entire network and allows you to add SDN capability to your network in an incremental fashion. So let's take a closer look at a couple of these use cases and applications that we've been able to demonstrate. First, I wanted to share the UCNC SDN application for Link. And so this application automates network policy and campus enterprise environment for Link. And so we worked closely with Microsoft on building this new SDN application which interfaces with Link server through their SDN API to automate policy across the network infrastructure to enable a better user experience with Microsoft Link. Essentially, what this does is it uses OpenFlow to push down rules that set traffic priority and also the path through the network in which a call traffic should take. So if 2 users are calling each other, whether it's voice, video, or application sharing, Link server informs the network control plane through the UCNC SDN application about information regarding the call type, the endpoints, and that information is used to push those policies down appropriately. And what you end up with is a much better user experience in terms of quality and responsiveness when using these types of applications. And this is really taking advantage of the power of SDN and that centralized control plane in order to inject more intelligence into the network. And the beauty of this solution is that it eliminates the manual device-by-device configuration that's traditionally required when configuring quality of service across the network. Essentially in this solution, and there's a live demo if you Google or YouTube this the title of this slide, you'll find a video demo that demonstrates how the solution works. And another example I wanted to share is our Sentinel security application, which won that Ethernet Innovation Award for Best SDN Solution this year. And this solution takes advantage of a few different parts of HP's intellectual property, including our HP Tipping Point business unit and ArcSight. And we actually have several customers who have deployed this solution in their production networks. And essentially how this solution works is Sentinel is an application that's running on top of our SDN controller, and it leverages this reputation database, RepDB, in the cloud, which keeps track of malicious websites. It has over 1 million threats with researchers that are constantly keeping that up to date. And essentially how it works is when a user comes on the network or a device, whether it's a server in the data center or a mobile device in a campus, if a user is trying to access a malicious site or if there's some type of infection or botnet, that traffic is redirected, either the DNS query or the first packet, IP packet, to the SDN controller, where Sentinel inspects that traffic against this dynamic real-time cloud database and determines whether that traffic is reputable or not based upon how the administrator has configured the application. And the traffic is then either blocked or allowed to continue via OpenFlow rule that's implemented on the infrastructure layer. So essentially this type of application is enabling new applications like bring your own device, BYOD, in a secure fashion, providing new visibility into threats. And some of the customers we have that have implemented this and deployed it in their networks have found that it's working much better than traditional solutions alone, such as antivirus or centralized content filtering. You essentially get this intelligence injected across the entire network through the use of OpenFlow. So one other thing I wanted to share here quickly is, one of the main questions that I get from customers is, this SDN sounds very compelling. I want to know how I can get started now. And really what we want to do is set the right expectations of the customers in terms of where the technology is at and where we're headed. And so now the direction we provide our customers is to really prepare yourself for SDN and start looking at your infrastructure and making sure that it's capable of supporting software-defined networking. And one way to do that is to ensure that devices and network devices that are being implemented today support open standards-based SDN via OpenFlow. And as we move through the rest of this year and into next year, we'll start seeing more and more commercial SDN applications being made available. In fact, HP's Sentinel virtual cloud network apps will be generally available in the first half of next year. And then as we move towards 2014 and 2015 is when we'll start seeing more of a developer ecosystem around SDN and more apps being developed by third parties, by the traditional networking vendors, etc. And by 2016, we really will start seeing more SDN in complete segments of certain networks. Maybe in the data center, you'll have a network that's more end-to-end SDN. And so just to wrap up here, I wanted to leave a few minutes for Q&A as well. Wanted to just reinforce, what HP's strategy is and our commitment to SDN and software-defined networking. We participate in several standards bodies, including the Open Networking Foundation, which is driving OpenFlow. We've been a leader in OpenFlow since 2007, since its inception, and we continue to participate within the ONF and on the working groups driving that standard forward. We also are a member of ETSI and are very focused on NFV and providing NFV leadership, as well as we're one of the top 5 code contributors to OpenStack and are very supportive of that project.
Great. Well, thank you so much, Steve and Mike and Toshal. We really appreciate your time. We have just a couple of questions for the group. Shouldn't take too long. It's because I know we're getting close to time. First up, when you say that there are 40 switches that now support SDN, do these include routers and switches from vendors like Cisco or Juniper, et cetera, or is it kind of consolidated?
Well, yeah, so I can take that question. The 40 switches are actually HP switches. So there, I think I can't speak for the other vendors, but HP has 40 switch models that are OpenFlow enabled today.
Okay.
I would just add that at the ONF Plug Fest, where we tested 1.3, there were 9 vendors who had OpenFlow 1.3 switches. So, we do see a pretty good movement of vendors moving towards 1.3, and so that's a good indication. But I can't really comment on exactly what vendors have what. I think you'd have to go to each individual vendor. Thanks.
Perfect. Another question we have is, are different versions of OpenFlow compatible?
This is Mike. I can take that one. Basically, the answer is no. The way the controller, the messages structures are different, and OpenFlow has changed through each version, where the functionality has been built off one another. However, you really would have a fairly small subset. So the only thing that I would say in terms of looking at, can I run multiple versions from OpenFlow in a network, it really depends on the controller. There was at least one controller at the ONF Plug Fest who implemented the ability to support multiple versions of OpenFlow, but it really is non-standard. So what I would suggest is, at least up through 1.3 is that, you'd be able to run a single version. You wouldn't necessarily want to run a 1.0 and a 1.3 on the same network. However, if you look at major versions like 1.3.1 versus 1.3.2, then I think that, you might be okay there. But again, it's very controller dependent.
Okay. Another question we have is, OpenFlow strictly for Ethernet switches and routers?
No. I mean, yes and no, but it's you can actually, and there is a project going on where you can be using OpenFlow for SONET-based switches and routers as well, but it's not strictly limited to Ethernet.
Yeah, I would just add that, the inception of OpenFlow was based on programming TCAMs, which are primarily Ethernet-based forwarding devices. So initially, yes. However, OpenFlow is being extended. There's a transport working group within the ONF that's looking at using OpenFlow as a control protocol for the optical layer. So, but most implementations you see today are all Ethernet. Optical is one of the emerging areas where OpenFlow is going, as well as wireless, like Wi-Fi is another area where it's going as well. We had our first Wi-Fi enabled device supporting OpenFlow at the last Plug Fest.
And there's a similar question, which is for is a project to extend SDN for SONET networks. Mike, do you want to comment on that?
Yeah, I mean, I think it's there are already extensions. As I was mentioning, OpenFlow is extensible. So on top of, I believe, 1.3, some of the vendors working through the ONF are working on defining commands and structures on top of OpenFlow to control transport layer, optical, like the what you were requesting. So I think certainly that's an area where it's emerging. I think the idea is that once you have a number of extensions that multiple vendors are supporting, you would work that back into a standard version. So like a version 1.4 or possibly a 1.5 may bring those back into standards-based OpenFlow instead of being based on extensions.
Okay. So I know we're right at time, but we have one last question left. So can SDN-based OpenFlow replace traditional MPLS and WAN, or is there any cost reduction by doing so?
That's quite a complicated question. I'd say, today I would say no, and that's primarily because OpenFlow, MPLS, as you look at it, has a lot of feature set. It's been built up over many years. What you have from OpenFlow today is just the ability to perform match and action on MPLS-based tags and headers. So potentially OpenFlow devices could be interworked with a traditional MPLS network. And I think most vendors are not looking at replacing MPLS as it stands today. That being said, OpenFlow continues to be expanded. Areas where it's kind of lacking are like OAM capabilities, and the config management group is working on developing OAM. So I would say, as I look at OpenFlow, I don't really look at it as replacing MPLS. I look at it as possibly, being interworked into the campus and the edge, and essentially being interworked with existing core MPLS networks. And using OpenFlow today, you can have a controller apply a label assignment and essentially, work with a existing MPLS core. So there's certainly a lot of work in this area. However, I wouldn't say that it's ready to replace any existing MPLS networks today.
Okay, sounds good. And we had one last question come in that we'll get to quickly. So how many flows does your controller support now, and what is the max rate to push flow to that switch?
I think, Steve, you may want to take that one from an HP perspective of control. Oh,
Steve.
Okay, so I'll take that one. What we're seeing in terms of the industry is that the flow rate is very much dependent on the switch. So the performance can actually vary greatly, and but since the flow tables are pushed down over TCP, you have TCP windowing, which will help manage this advertising of the flows, as well as you have the barrier message, which the controller can use to ensure that the switches have processed the flows. So with those mechanisms, Toshal, you may want to comment from a testing perspective what kind of rates we've seen.
Right. So we have seen processing rate as low as 100 to several thousands flows per second as well. Similarly, we have seen a switch supporting as low as 4,000 flows to 1 million flows as well. So it all depends upon whether, it goes back to the slide Mike shared, whether your switch is doing, it's a hybrid switch, or it's a software switch, or it's a purpose-built switch. In terms of how many numbers our controller support, we have solutions to cater for all the things I mentioned just now. So we have a test board or hardware which can allow you to validate a small scale as well as to high scale setup as well. If you would like to know more about that, there's a lot of information available on the Ixia website in terms of what our controller is capable of doing.
One other comment is that within the ONF we're working on standardizing it, but Ixia has a flow table benchmarking a quick test, which will allow you to benchmark how many flows the device is able to handle. But then the ability to handle those flows is one thing, but the ability to actually what's the forwarding performance once you're holding those flows is another thing. And that's where you can quickly determine if those flows are in hardware or in software. And so it varies greatly per implementation.
Well, great. Thank you guys so much for your time, and thank you everybody for joining us today for the webcast. I hope you got a lot out of it. I think it was some really good information. So you've seen up on your screen, there's a couple of web pages that can take you to some more information, and also don't hesitate to reach out to Ixia should you have any further questions. So thank you again for your time today, and everybody have a good rest of your week.